I'd like to welcome you all to a distinguished lecture on scheduling theories for cyber-physical systems by Sanjoy Baruah from University of North Carolina, Chapel Hill. Sanjoy is a professor in the Department of Computer Science at the University of North Carolina, Chapel Hill. He received his PhD from the University of Texas at Austin in 1993. Song Han is from there. And by the way, my daughter is from there, so Longhorns. He received his PhD from the University, UT Austin. His research and teaching interests are in scheduling theory, cyber-physical systems design, and resource allocation and sharing in distributed computing environments. He's a fellow of the IEEE and the recipient of the 2014 Outstanding Technical Contributions and Leadership Award of the IEEE Technical Committee on Real-Time Systems. Oh, Sanjoy?
Thank you. So thank you very much, Krishna, all of you, for this opportunity to visit this beautiful campus. It's a truly beautiful campus. And for this opportunity to tell you a little bit about my work. I also hope that I will have an opportunity to learn a lot about what's going on here, about the work that's happening at this center later today, at this institute, pardon me. So as Krishna mentioned, my research interests and activities are in figuring out how to apply results from scheduling theory to the development of safety-critical computer systems. In the context of computer systems, scheduling is concerned with the efficient allocation of computational resources that may be available in limited quantities in order to optimize certain system-wide objectives to achieve desired system-wide goals. Now, scheduling theory has always, traditionally, had an important role to play in the process of designing, analyzing, and implementing safety-critical real-time computer application systems. I've spent 20 years of my research career working on this. But what I would like us to do during this presentation is examine the evolving role of scheduling theory within the recently emergent and increasingly important discipline of cyber-physical systems. The main point I will try to make during this presentation, the central thesis that I will attempt to establish, can be stated as follows. In developing safety-critical computer systems, we have traditionally had two important goals. We, of course, require these systems to be correct. In addition, we would like to be able to ensure that they can be implemented in a resource-efficient manner. Over time, due to a variety of factors that we will examine, we have come to focus more on ensuring correctness, letting considerations of efficiency recede to the background. However, some current and likely future trends in technology argue in favor of reintegrating efficiency considerations into the process of developing these systems. And it seems that the current trend in embedded computing towards mixed criticality systems, in which less critical functionalities coexist upon a shared platform with more critical ones, offers us an opportunity to achieve such reintegration. So let's examine this thesis in somewhat greater detail. The discipline of real-time computing has its origins in the application domains of defense, space, and aviation. It should be evident that these are all highly safety-critical domains that place a great premium on correctness, since the consequences of incorrect system behavior is potentially catastrophic, causing a loss of life, a perhaps significant loss of property. Additionally, early systems in all these domains were characterized by the fact that they had very limited computational capabilities upon which to implement these functionalities. We therefore had to design our real-time systems to not just be correct, but be implementable in a resource-efficient manner. In the early years of the discipline of real-time computing, these twin goals were achieved by keeping things very simple. Real-time systems were required to be very simple, responsible only for very simple, highly repetitive kinds of functionalities. They were often implemented as carefully handcrafted programs, typically consisting of little more than straight-line code embedded within an infinite loop, executing upon very simple, custom-designed to be highly predictable platforms. These early systems were very successful in achieving the twin goals of correctness and efficiency. But things soon grew complicated. Our success made us ambitious. The requirements we placed upon our real-time systems grew increasingly more complex. The implementation platforms needed to become more powerful. These more powerful platforms were not as simple, as deterministic as the earlier custom-designed platforms. It soon became impossible for a single developer or a team of developers to reason about the correctness of a large, complex system in all its gory detail. Instead, abstractions had to be introduced that could highlight the important, the salient features of these systems, while concealing the less important features, the less relevant aspects. But of course, notions such as relevance and importance lie very much in the eye of the beholder. In figuring out which aspects of a system's behavior should be highlighted and which ones concealed, the real-time and embedded systems community were very strongly influenced by the increasingly central role that computers are coming to play today in controlling critical infrastructure. Think of a modern car or an airplane and think of how much of the functionality on board is controlled today by computers. This trend towards increased computer control is only accelerating with the worldwide enthusiasm we see today for cyber-physical systems or the Internet of Things, in which already complex embedded devices are interconnected into vast and vastly complicated networks, which are then entrusted with autonomous responsibility over significant fractions of critical infrastructure. Now, it should be evident that correctness remains a prime concern in the development of such highly safety-critical systems. Additionally, as these systems become larger and more complex, it is proving increasingly more difficult to ensure correctness, particularly to the very high levels of assurance we desire of functionalities that can do so much harm if they go wrong. So this is how matters stand concerning correctness. What about efficiency? There things are looking better. Significant advances in computer architecture and chip manufacturing, compounded over decades as codified by Moore's law, means that today we can provide vast amounts of computing capability at relatively low cost to individual embedded devices. So this is how things stand. On the one hand, correctness is becoming harder to achieve and more important to achieve. On the other, thanks to Moore's law, we can provide lots of computation, which means that ensuring efficiency of implementation is perhaps less crucial. Facing these realities, these facts, the real-time and embedded systems community made the rational choice and went in for design abstractions that focus primarily on ensuring correctness, letting considerations of efficiency recede to the background. Perhaps one of the most important developments in this regard was the introduction of what is called the synchrony assumption, which essentially attempts to separate considerations of functional correctness from considerations of timing correctness by introducing the concept of logical time or rounds and making the assumption, the simplifying assumption, that actions such as execution of code will take zero logical time. Physical time, the thing that gets measured in our clocks, was instead dealt with via other abstractions such as timed automata, timed Petri nets, and the like. These and other abstractions formed the basis for a number of model-based design methodologies for safety-critical systems. These model-based design methodologies which are built upon very firm formal foundations and often come equipped with excellent tool support, have proved very popular and today find widespread industrial usage, particularly in the safety-critical application domains of automotive systems and aviation. Now, this is a good thing, but it is important to understand that the end product of the process of developing a system using one of these model-based design methodologies is, as the name implies, a model of the system you seek to obtain, not its implementation, not its physical realization on metal and silicon. The fact of the matter is, we do not yet know today how to obtain resource-efficient implementations of systems that are developed using these model-based design methodologies and therefore specified using a model-based formalism upon today's very powerful but highly non-deterministic, highly unpredictable platforms. In the absence of such knowledge, current industrial practice is to rigorously apply these model-based design methodologies to come up with a model of the system we seek to implement, and then depend upon ad hoc techniques and rules of thumb to obtain an implementation, and apply tremendous resource over-provisioning on the implementation platform in order to ensure that these correctness properties get preserved in the implementation. Thus far, it can be stated that this approach has served us well. The discipline of real-time computing is a very successful one. Safety-critical systems industries are thriving. But throughout, there is this uneasy feeling that this approach has run its course, that it will prove inadequate as we seek a further exponential increase in the complexity and diversity of the kinds of systems we are seeking to build. Perhaps the main reason why there is this feeling that it is time now to reintegrate considerations of efficiency into the design of safety-critical systems is best explained by appealing to a widely observed phenomenon in system implementation that you may have come across that is often called the window of scarcity argument. Let me attempt to illustrate this visually. In this two-dimensional space, I will represent any system implementation according to the complexity of its specifications and the computational capabilities of its implementation platform. Now, this is all rather vague and imprecise, but informally speaking, the farther up you move along the y-axis, the more complex and computationally demanding the specifications become. The farther out you move along the x-axis, the more powerful, the more capable the platform is. Now, upon any given platform, there are some system specifications that can easily, trivially be implemented. The computational capabilities needed in order to satisfy these specifications are so modest relative to the capabilities of the platform that any specific implementation, even a hopelessly naive one, will easily satisfy them. On the other extreme are those specifications that cannot possibly be implemented upon this platform. Lower bound theories, impossibility proofs, and other techniques can be used to demonstrate that the platform is simply not powerful enough. Between these two extremes lies an interesting class of specifications, those that can indeed be implemented upon this platform, but only by carefully marshalling the resources on the platform and cleverly sharing these resources amongst competing demands that are made upon them. So now, as platforms become more powerful as they have over time, the precise class of specifications that fall into each of these three categories will change. But this general phenomenon of all specifications being classifiable as trivial or challenging or impossible to implement will be expressed across all platforms. We refer to the middle part of this diagram, the part I've shaded here in, I guess, rather garish yellow, we refer to as the window of scarcity. Points within the window of scarcity correspond to system implementations that are enabled only by careful consideration of resource allocation, scheduling, and synchronization issues. In other words, every system specification that falls within the window of scarcity is enabled only by the application of often advanced principles from scheduling theory. So, as I had mentioned earlier, current practice in developing safety-critical systems is to depend upon these model-based design methodologies to come up with a specification of the system, a model of the system, and rigorously demonstrate the correctness of this model. Once we have done this, we need to find an implementation platform. Current practice is essentially to move out parallel to the x-axis until one exits the window of scarcity, at which point it is trivial to obtain an implementation. If, however, we had paid attention to resource allocation issues, to optimization issues, to implementation efficiency issues from the very beginning, we could have perhaps implemented the system upon a less computationally capable and therefore perhaps less expensive platform. We refer to the difference between the computational capabilities of the platform we ended up using and those of this minimal platform as the scheduling penalty that we are being required to pay as a consequence of having chosen to ignore efficiency issues throughout the design process up until this last step. Thus far, the scheduling penalty has been a cost we have been willing to pay, particularly when you contrast the increasing importance of and difficulty in achieving correctness on the one hand against the fact that, thanks to Moore's law, the actual dollar cost associated with this scheduling penalty is not unbearably large. So what changes moving forward? Why do we believe this approach is not viable as we seek a further increase in the complexity and diversity of the systems we seek to build? Well, as I just stated in 2 words, system complexity. The complexity of the systems we seek to build now, moving forward, are enormously, exponentially greater than the complexity of the systems we have been building earlier. And as we move further away from the origin in this diagram, the size of the scheduling penalty grows exponentially. This is because the features that are to be found on modern platforms that actually allow us to move so far out along the x-axis, features such as heterogeneous multi-core CPUs, multiple levels of memory, including on-chip cache and off-chip memory, complex networks on chip, deep pipelining, speculative out-of-order execution, and the like. These features, which have been introduced over the past few years and allow us to come up with enormously more powerful platforms, these features must be used very carefully if they are to yield any appreciable performance benefit. Incorrect or even careless use of these features results in a tremendous performance degradation, which in our diagram gets expressed as a larger scheduling penalty. The size of the scheduling penalty has grown at a truly tremendous rate in recent years. It's perhaps more accurate to think of this diagram as being plotted on a logarithmic scale to indicate the exponential increase in the size of the scheduling penalty over the past few generations of computer hardware. It is this cause, this rapid exponential growth in the size of the scheduling penalty over the past few years, that makes it no longer viable to continue to ignore the scheduling penalty in implementing safety-critical systems. The dollar cost associated with doing so is simply too large now, Moore's law notwithstanding. Additionally, even if we were willing to ignore the dollar cost, if we were working, for example, in application domains that are not very sensitive to cost, I'm thinking of some defense applications and some space applications that are characterized by the fact that we built very few devices, which means that the cost of the platform is not a dominant factor. Even in such application domains, swap considerations, the size and weight of the implementation platform, and the power, or more accurately, the energy that gets consumed by it, argue in favor of attempting to reduce the scheduling penalty. Let's first consider platform size and weight. Many embedded domains are characterized by a need for mobility. Cars, planes, spacecraft need to be able to move around. For such devices, for such domains, the form factor of the implementation platform, its size, its shape, its weight, can often mean the difference between a completely viable, reasonable design and a hopelessly infeasible one. Energy concerns come in many flavors. First, there are environmental considerations. As embedded systems become more prevalent, they become responsible for consuming a larger fraction of the energy that we consume as a society. If we are to reduce our energy consumption, reduce our carbon footprint, these devices must make more efficient use of the energy that is available to them. Energy consumed gets expressed as heat generated. This heat must then be dissipated, often at great cost. The consequences of this heat, the rise in temperature, the subsequent change in thermal properties, and the impact they have on the system performance and behavior must all be dealt with. Devices that are characterized by a need for mobility cannot be tethered to the power grid. They must carry their energy sources around with them, either as batteries or as energy harvesting systems. So for such devices too, the efficiency with which they are able to use the energy that is available to them can mean the difference between a viable and an infeasible design. Summarizing the narrative that we've been going through thus far, in the early years of the discipline of real-time computing, we were equally concerned with making sure that our systems were correct and they were implementable in a resource-efficient manner. Over time, thanks in large part to Moore's law, we could let concerns of efficiency fall back a little bit. We focused primarily on correctness. One important implication, consequence of this, was that scheduling, which is concerned primarily with efficiency of implementation, ceased to become the foundational cornerstone for new ideas for developing safety-critical systems. This role was instead taken over by formal methods, which are concerned primarily with provable correctness. Today, however, due to both cost and swap considerations, efficiency has once again moved to center stage, which means we must again be concerned with ensuring efficiency. And this brings me to the fourth and final clause of the thesis. The move towards mixed criticality systems offers us an opportunity to achieve such reintegration of efficiency considerations. So let's examine this clause in somewhat greater detail. Let's first attempt to understand what mixed criticality systems are and why they've come about. To understand this, let's revisit what we have discussed about modern safety-critical systems. We said that such systems have become larger and increasingly more complex, which means they are characterized by increasing computational requirements. They must therefore be implemented upon advanced platforms. However, the most advanced, the most powerful platforms available today are those that have been developed for providing optimized average case performance, not tight bounds on worst case behavior. Such platforms are therefore generally characterized by very non-deterministic, very unpredictable runtime behavior. Despite this fact, since our safety-critical systems do perform functions that are very critical, they need to have their correctness validated to very high levels of assurance, to very great degrees of confidence. Since these systems are so complex and the implementation platforms so non-deterministic, the only manner in which we can ensure correctness to the desired high levels of assurance is by tremendous over-provisioning of computational and other platform resources during this implementation phase. Let me illustrate. Consider the simple operation of adding two integer variables and storing the result in a third on the PowerPC 755, which is a general-purpose processor optimized for use in embedded devices that finds widespread use in some safety-critical devices, including some Airbus aircraft. An Airbus study from several years ago had concluded that this operation may execute in as few as 3 cycles, and generally, almost always takes not many more than 3 cycles to complete. However, pathological worst-case conditions have been identified under which the same operation may take as many as 321 cycles to complete. This means that if this operation were to form part of a highly critical functionality whose correctness must be validated to a very high level of assurance, then, under the admittedly unlikely or forbidden circumstance that we don't know very much about the runtime context within which this operation is executing, we are required to reserve as many as 321 cycles for this operation, despite knowing full well that almost always most of these reserved resources will end up being unused. To highlight the fact that platforms have been becoming more non-deterministic with the passage of time, let me point out that an earlier generation of Motorola's general-purpose processors had implemented the same operation to take exactly 20 cycles under all circumstances. As you can see, the best and average case performance have improved significantly. The cycle count has gone down, the clock frequency has gone up, which means the duration of each cycle has gone down a lot as well. But the spread between the worst case and the best case behavior has changed from a factor of 1, which means absolute determinism, to a factor of over 100. Nor is this an outlying example, a pathological situation. Similar examples abound throughout safety-critical system design. I remember attending a talk by a research engineer from Thales, the French defense manufacturer, who was describing the manner in which resource reservations can get done in some avionics applications within the Thales family of companies. Apparently, very careful analysis, including perhaps cycle counting, is done in order to figure out how much computation a particular piece of code will require. Once this is determined, this is the worst case bound, a safety margin gets added on top before making the actual reservation. For some highly critical avionics applications, this safety margin is actually a multiplicative factor of 10. This means that even in the worst case, the system developer fully expects that no more than 10% of the reserved resources will actually be used. The remainder of the reservations are being made only in order to be able to validate the correctness of the system at the desired levels of assurance, probably, almost certainly given the numbers here, for the satisfaction of statutory certification authorities. As you know, certification is a big deal in the aviation industry. The bottom line, current practice of ensuring correctness of critical functionalities at the high levels of assurance upon today's very non-deterministic platforms means that during runtime, these platforms tend to see very poor resource utilization. As we had argued earlier with the window of scarcity argument, this is proving increasingly unacceptable. One approach that the real-time and embedded systems community is taking towards dealing with this dilemma, towards resolving, bridging this gap, is by moving towards what are called integrated computing environments. Architectures such as AutoZAR in the automotive industry, integrated modular avionics, IMA, within aviation, that attempt to co-implement upon a shared platform functionalities of different degrees of importance or criticalities. Informally speaking, the idea here is that significant resource over-provisioning will continue to be used in order to validate the correctness of the highly critical functionalities at their desired high levels of assurance. But since, as we had argued, most of these resources are unlikely to actually end up being used during runtime, some of them can be reclaimed at system design time itself using techniques that we will elaborate upon in a moment, and used to make performance guarantees, albeit at low levels of assurance, to the remaining less critical functionalities. So this is the idea. Let me illustrate by means of a contrived, very simple example. Suppose that I had a piece of highly safety-critical code whose execution is triggered by some external event that may occur repeatedly. This code takes 2 time units to execute, and it is required that its execution complete before the next occurrence of the triggering event. We seek to validate an implementation of the system prior to actual deployment. In order to do so, of course, we must first build a model of the system's execution during runtime and analyze this model in order to convince ourselves that the system is indeed going to behave correctly during runtime. But in order to have a good deal of confidence that the conclusions we draw based upon the analysis of the model will hold for the actual physical system, we must be fairly conservative in the manner in which we build this model. We must build some safety, some pessimism into the modeling process. So, observe that the events that trigger the execution of the code, these external interrupts, are external to the system being developed. They occur in the environment within which the system is operating, and therefore are not under the direct control of the system developer. So a system developer must make certain assumptions about the occurrence of these events before constructing their model. Let us suppose that our system developer carefully and extensively observed the environments within which they would like their system to operate. Based upon these observations, they conclude that for the kinds of environments within which they expect the system to operate, successive triggering events occur no sooner than 20 time units apart. This is an assumption. With this assumption in place, the system response to these triggering events can be modeled using an abstraction known as a sporadic task model, more colloquially as a Liu and Leyland task model, that has been extensively studied in the real-time systems community. A sporadic task is an abstract entity that is characterized by two parameters, a worst-case execution requirement parameter and a minimum inter-arrival separation parameter that is also sometimes called the period of the task. Such a task, such an entity, is assumed to generate an unbounded, potentially infinite sequence of pieces of work that are known as jobs that are required to be executed. The jobs generated by a sporadic task with worst-case execution requirements C and period T must satisfy these constraints. The first job generated by this task may arrive at any instant in time. Subsequent arrivals must be separated by at least T time units. Every job has an execution requirement that does not exceed this parameter C, and this execution must complete within a deadline that occurs T time units after the arrival of the job. Some added terminology. We use the term utilization to denote the ratio of the worst-case execution requirement of a task to its period. Informally speaking, you can convince yourself that the utilization of a task denotes a tight upper bound upon the fraction of the computing capacity of a single processor that may need to be devoted to executing work that was generated by this particular task. So, with the assumption that successive triggering events occur no sooner than 20 time units apart, it's easy to see that the system response to these triggering events can be modeled as a sporadic task with worst-case execution requirement 2 and period 20. Its utilization, therefore, is 2 divided by 20, or 0.1. Now, 10% utilization of a processor is very low. Let us suppose that our system developer, therefore, decided to implement upon the same processor another piece of real-time code, this one not safety critical, that can be modeled as a sporadic task with parameters 5 and 6 respectively. The utilization of this task is 5/6, or about 84%. Observe that the sum of the utilizations of the two tasks is less than 100%. There is a well-known result in real-time systems, real-time scheduling theory, which says that the earliest deadline first scheduling algorithm, which chooses for execution at each instant in time the currently active job whose deadline is the closest in the future, is able to schedule upon a single processor, that is preemptive, preemptivity is important, any collection of independent sporadic tasks whose utilizations sum to less than 100% in such a manner that every job of every task will always complete by their deadlines. Applying this result, we can conclude that if our system developer had chosen to schedule their system during runtime using EDF, using earliest deadline first, all system deadlines would be met. We would have a correct system design. This is good, but it is important to understand that the correctness of this conclusion rests very strongly upon the validity of the assumption that successive triggering events occur no sooner than 20 time units apart. And that is an assumption that the system developer made. Let's study the implications of that assumption by extending our example somewhat. Let's assume that for our system, it is required that the correctness of the critical functionality, that is, the response to these external events, must be validated by some statutory certification authority that is not necessarily willing to accept the system developer's assurances that successive triggering events will occur no sooner than 20 time units apart. Instead, this certification authority does their own analysis, observes the kinds of environments within which the system might operate themselves, and based upon their analyses, concludes that for the kinds of environments within which certification is being sought, the best that can be said is that successive triggering events will occur no sooner than 10 time units apart. So, from the perspective of the certification authority, the system response to these triggering events is modeled as a task with parameters not 2 and 20, but 2 and 10. The utilization of this task, again from the certification authority's perspective, is therefore 2 divided by 10, or 20%. The sum of the utilizations of the two tasks now exceeds 100%, which means that no scheduling algorithm, EDF or something else, can possibly guarantee to schedule the system upon a single processor such that all job deadlines will always be met.
Now, you assume that the context switching is 0, right?
Under the simplifying assumption that context switching is 0, we still have the fact that it exceeds 100%. So the assumption that context switch is 0 was being made implicitly in the previous situation when I said the utilizations did not exceed 100%. But that is correct. That is an assumption that was made there. We will address that a little bit later, perhaps, by talking about how you deal with that assumption. This means, given this result, that if we were to schedule our system, if our system developer had indeed chosen to schedule the system during runtime using EDF, the earliest deadline first algorithm, and then they had submitted this design for certification, the certification authority would have not passed the system would have failed certification. Of course, if the only objective of the system developer was to obtain certification, what they should have done was instead chosen to schedule the system using what is called a fixed priority scheduling algorithm during runtime. Assign greater priority to work generated in response to these external triggering events, to work generated by the critical task. Such a design would indeed pass certification upon a preemptive processor because the certification authority is only concerned with whether the critical code executes correctly. And it's a preemptive processor, so the certification authority concludes that whenever an external interrupt occurs, the fixed priority scheduling ensures that whatever is executing upon the processor gets preempted and the critical code gets to execute. This critical code will complete within 2 time units. The next interrupt, under the certification authority's own assumptions, will not occur until 10 time units have elapsed, which means that the code did indeed execute correctly. So, this design passes certification, things are good. The problem with fixed priority scheduling, of course, is that even in the event of the system developer's assumptions turning out to be correct, successive triggering events occurring no sooner than 20 rather than just 10 time units apart, even under those circumstances, we may end up missing deadlines, although, of course, all missed deadlines would be non-critical. Suppose, for example, that both the critical and the non-critical code tasks had jobs generated at the same instant in time. Under fixed priority scheduling, the critical code would get to execute for 2 time units, leaving only 4 time units for the non-critical task to complete 5 units of execution by its deadline, which, of course, it cannot do. By contrast, EDF would have scheduled the system correctly. So examples and situations such as this, where by using different strategies, we could come up with a scheduling algorithm that satisfies different requirements, have motivated the real-time systems community in recent years to propose a somewhat stronger notion of correctness for real-time algorithms that is called mixed criticality correctness, or MC correctness. In the context of this example, illustrative example that I have put up over here, a mixed criticality correct, an MC correct scheduling algorithm is an algorithm that, for use during runtime, that does not claim to know beforehand what the minimum inter-arrival separation between successive triggering events is going to be, but can nevertheless make the following performance guarantee. If during runtime it turns out that the system developer's assumptions are correct and successive triggering events occur no sooner than 20 time units apart, then all jobs of both tasks will complete by their deadline. If, however, during execution it turns out that the system developer's assumptions were incorrect, but the certification authority's assumptions were correct, that is, successive triggering events may occur sooner than 20 time units apart, although they will not occur sooner than 10 time units apart, even under those circumstances, it should remain the case that all critical tasks, all critical jobs will complete by their deadline, although non-critical jobs may fail to do so. In other words, we want a single algorithm that possesses the good properties that we had seen earlier for EDF and fixed priority scheduling. Over the past 4 or 5 years, the real-time systems community has devoted considerable effort at better understanding this concept of mixed criticality correctness, and have come up with some very innovative techniques and methodologies that allow us to derive MC-correct scheduling algorithms for particular situations. We can apply those techniques to our very simple example and come up with an MC-correct runtime scheduling algorithm that would behave as follows. The algorithm will start out scheduling the system using the EDF approach, the earliest deadline first approach. However, the manner in which it assigns deadlines to jobs for the purposes of scheduling is somewhat peculiar. If a job of the non-critical task arrives, it gets assigned a deadline equal to its arrival time plus the period parameter of the task that generated it, or 6. This is exactly as we would have expected. If a job of the critical task arrives, however, it gets assigned a deadline equal not to its arrival time plus its period as estimated by the system developer, or 20, nor a deadline equal to its arrival time plus its period as estimated by the certification authority, or 10. Rather, it gets assigned a deadline equal to its arrival time plus the number 7. Where did this number 7 come from? Well, right now, I plucked it out of thin air. As I said earlier, techniques have been developed within the real-time systems community over the last few years that allow us to formally derive MC-correct scheduling algorithms. I applied some of these techniques to this example beforehand, and the result that came out as a consequence of applying those techniques is this number 7. I do not plan to discuss during this presentation exactly why this number came about. For those of you who are interested, I'd be happy, of course, to explain it to you.
Is it some of the 2 C's by any chance?
In this case, accidentally, yes, but there's a somewhat more involved derivation that requires us to get this. But yeah, sure, 5 plus 2 gives us 7 is not a bad estimate, yeah? So in essence, there is this technique. This was an excellent first iteration of coming up with this technique, which gives us this particular scheduling algorithm, all right? During runtime, of course, the algorithm must monitor the occurrence of these external triggering events to make sure that they don't arrive too soon. If during runtime, the algorithm determines that successive triggering events have occurred sooner than 20 time units apart, which means that the next triggering event occurred before 20 time units had elapsed since the previous triggering event, under those circumstances, the algorithm immediately knows that the assumptions made by the system developer were invalidated, and therefore the algorithm is no longer required to ensure the correctness of the critical or non-critical jobs. It therefore immediately moves to a fixed priority scheduling algorithm and begins executing the critical jobs in preference to the non-critical ones. It can easily be shown rigorously that this particular scheduling algorithm, a runtime scheduling algorithm, does indeed possess the properties of mixed criticality correctness for our example. If successive triggering events occur at least 10 time units apart, all critical jobs complete by their deadlines. If successive triggering events occur at least 20 time units apart, all jobs, critical and non-critical, complete by their deadlines. I guess I should address just, in response to Krishna's question, the thing about making the assumption that preemptions cost us nothing. That is definitely an assumption that's been made over here to state that earliest deadline first has this utilization test, which says that if the sum of the utilizations does not exceed 100% of a processor capacity, the processor is schedulable. The task system is schedulable to always meet all deadlines. That makes the assumption that preemptions cost nothing. That assumption is dealt with in practice by making the following observation. Any EDF schedule, and this is rigorously demonstrated, will see the number of preemptions across the entire schedule not exceeding the number of individual jobs. In other words, the number of preemptions that you will see in a schedule is no more than the number of jobs in the schedule. Therefore, in implementing preemptive EDF, the typical practice is to inflate the execution time of each individual job by the amount of time it would take to implement a preemption. So when I said that the execution time is 2, perhaps the assumption, the reality, the fact on the ground was that the execution time was 1.95, and to implement a context switch takes 0.05 time. And that assumption is how we deal with this, practice is how we deal with the simplifying assumption that preemptions take no time. Okay? So this, stepping back for a moment, was one example, one illustration of applying the principle of mixed criticality analysis to obtain a resource-efficient implementation of a highly critical functionality implemented upon a platform with some shared, less critical functionalities. Let me provide another illustration by drawing your attention to one particular attribute I have used in describing this example, the execution time of a piece of code. What exactly is this execution time supposed to represent, and how do we assign it a value? In scheduling theory, at least in real-time scheduling theory, jobs are typically modeling the execution of a piece of code that has been written by some software developer, some real-time systems engineer, in order to achieve some desired functionality for their real-time system. Its execution time therefore denotes the maximum duration of time this piece of code would take to execute upon its implementation platform, a parameter that is commonly referred to as the worst case execution time, or Wset for that piece of code. How do we determine these things? Well, once a piece of code has been written and validated for functional correctness, in other words, once we've agreed that it does what we want it to do, it gets subject to analysis by a tool known as a worst case execution time analysis tool. This tool accepts as input the code and the specifications of the platform upon which this code is to execute, does some often fairly non-trivial analysis, and determines this Wset parameter. So what I'd like us to do now is take a closer look at the internal workings of this tool. Some of you may be familiar with this graphic, very widely cited graphic, from a paper co-authored by Reinhard Wilhelm and a bunch of other luminaries in real-time systems. It shows the distribution of runtime for a single piece of code that is repeatedly executed upon a modern, non-deterministic platform. As you can see, there's considerable variation in this runtime. For this piece of code upon this platform, the true worst-case execution time, the parameter that this tool seeks to determine, is this. However, for non-trivial pieces of code implemented upon non-deterministic, unpredictable platforms, the exact value of this maximum duration is very hard, maybe impossible to determine precisely. Think about it this way. If I give you a piece of code, even if the platform were completely deterministic, in order to know what the maximum duration of time this code would take to execute, you would be solving, if the code were completely general, the halting problem, a famous undecidable problem in computer science. This throws on top of this non-determinism on the underlying platform. So this value is basically not determining worst-case execution time precisely is essentially an unsolvable problem. So what these tools generally tend to do is determine upper bound on the true worst-case execution time. And of course, it is the nature of upper bounds that the higher the level of assurance you seek in an upper bound, the greater the degree of confidence you want to have that the value you assign to an upper bound is indeed a true upper bound, the larger that bound needs to be. So very conservative tools have been developed and are sold that are able to estimate these upper bounds to very high levels of assurance, to very great degrees of confidence. Such conservative tools are typically based upon static analysis of the code. Carefully examine the code in order to identify some, perhaps unrealizable but guaranteed safe, worst-case execution path through the code. Subject this path to very careful analysis under extremely conservative assumptions concerning, for instance, interference from other processes or the state of shared resources such as cache, to come up with a wildly pessimistic but guaranteed safe upper bound on the duration of time this code would take to execute. If the code were even somewhat complex, this upper bound might actually end up being infinity. We cannot really bound the duration of runtime for this code. A less conservative tool may be measurement-based. We instrument the code, we simulate its behavior in a laboratory under a wide range of conditions, representing what the system developer believes are all the conditions the code would encounter during actual runs, take the largest observed runtime, and perhaps inflate it with an additional safety margin. the resulting value you get is likely to be a whole lot smaller than the one determined using static analysis. But there is a slight chance that this bound is actually incorrect, that you undercounted the true maximum duration of time the code could take to execute, simply because the experiments, the simulation experiments, failed to expose the true worst-case behavior of this code. So this is one important fact to keep in mind in designing in using these worst-case execution time analysis tools. The same piece of code may be characterized with different Wset parameter values by different tools, and this is because we can trust the results of these tools to different degrees of assurance. Another problem, or another fact to keep in mind in using Wset analysis tools, is that for certain pieces of code upon certain platforms, the true worst-case behavior may be extremely unlikely to occur in practice. In other words, the distribution of runtimes may actually look like this. We've already seen an example, right? Adding two integer variables on the PowerPC 755. I said, for that, the best and average case behavior is close to 3 cycles. The worst case behavior, however, is 321 cycles. A truly conservative worst-case execution time analysis tool that could actually bound the maximum amount of time this code would take to execute must characterize this piece of code with a Wset parameter value no smaller than 321 cycles. But a less conservative tool may choose, despite knowing this fact, to characterize this tool with a smaller Wset parameter value. And this is okay, provided the user of the tool, the person who's using this tool to develop their system and validate its correctness, is aware that under certain extremely rare circumstances, the bound of the tool may be violated, and therefore, they build some fault tolerance, some robustness into the code they are writing to deal with those exceptional circumstances. To summarize the points I've been saying about worst-case execution time analysis tools, when I first put this diagram up and stated that such a tool accepts as input code and platform and tells us the maximum duration of time the code would take to execute upon the platform, I was simplifying things. In actual fact, these tools determine upper bounds on the actual maximum duration of time the code would take to execute. Different tools have been devised that are able to estimate this upper bound at greater or lesser levels of assurance to smaller or larger degrees of confidence. A very conservative tool would give us a bound that we can trust to a very high level of assurance. Such a bound is likely to be extremely large for many pieces of code. However, we need to use such a large bound in order to validate the correctness of highly critical functionalities. Less conservative tools will characterize the same piece of code with a smaller Wset parameter value. We have less confidence in the correctness of the bound produced by such a tool, but the confidence we have may be adequate for validating the correctness of less critical functionalities. And this brings us to the multiple worst-case execution time mixed criticality scheduling problem, which was, historically speaking, the first scheduling problem to be studied at great depth from a mixed criticality perspective by the real-time systems community. This problem appears in a paper that was presented by Steve Vestil at the IEEE Real-Time Systems Symposium in Tucson, Arizona in the year 2007. In those days, Steve was working for Honeywell on a validation of avionics software. I'm going to describe a somewhat simplified version of the problem discussed by Steve. Let's suppose that we have a real-time system that is specified as a collection of independent jobs. Each job is designated as either being critical or non-critical. Each job is further characterized by two worst-case execution time parameter values. A very large value denoting its worst-case execution time is estimated by a very conservative tool, and a somewhat smaller value denoting its worst-case execution time is estimated by a less conservative, perhaps measurement-based tool. Given the specifications of such a system, our obligation is to come up with a single, fully deterministic strategy for executing the system during runtime, which possesses the following properties. If during runtime it turns out that the less conservative Wset analysis tool was correct, and each job would indeed complete execution if allowed to execute for up to the smaller of its Wset parameter values, Under those circumstances, it should be the case that all the jobs will be executed correctly to complete by their deadline. If, however, it turns out that the less conservative Wset analysis tool was incorrect, some jobs are unable to complete despite being allowed to execute for up to the smaller of their Wset parameter values. Even under those circumstances, it should remain the case that all those jobs designated as being critical will complete by their deadlines, although the remaining jobs may fail to do so, provided, of course, that the more conservative tool was indeed correct, that each job does complete if allowed to execute for up to the larger of its Wset parameter values. So as I mentioned, this problem was introduced by Steve Vestil in the year 2007 to the real-time systems community. The community immediately recognized the importance of this problem. They understood that this problem was getting to the heart of, was in some sense distilling the essence of some very important, perhaps existential challenges that the community were facing at that time. They therefore responded to the introduction of this problem with great enthusiasm. Some top researchers in real-time systems began working on mixed criticality systems. A number of very innovative and ambitious projects were initiated and received surprisingly generous levels of funding from government and from government funding agencies and industry, both in the United States and in Europe. In short order, this topic, mixed criticality analysis, became one of the important focal areas of the topic of the discipline of real-time computing. Song and I are both attending this conference in Europe on real-time systems, one of the premier conferences in the discipline next week. I looked at the program today. It's a very selective conference, single track, 3 days. As I said, I looked at the program earlier this morning, actually. There's one keynote in the entire conference, which is devoted to mixed criticality systems. 5 of the 25 papers that were selected for presentation at the conference, peer-reviewed, selected by a program committee. 5 of the 25 papers have the phrase mixed criticality in the title itself. This has really become a foundational topic, one of the focal topics of real-time systems today. In fact, sorry?
I mean, I serve as the RTSS TPC member, and when I take a look at the paper submissions, there's too many papers on mixed criticality systems, on different aspects of the system.
Indeed. In just about every aspect of this topic, as they relate to safety-critical system design. It really is a hot topic. One of my very close research collaborators and very good friend, Alan Burns at the University of York in the UK, maintains an online survey of recent research, of current research that he considers important on this topic. Again, he updated his last, he says, in December 2014. At that time, he cited 245 references that, again, he considers relevant. The vast majority of these references are dealing with various aspects of the problem identified by Steve. I definitely do not intend to talk to you about these 245 references during this presentation, which I'm about to wrap up. But for those of you who want a snapshot on the current state of the art of this very important and interesting topic, I highly recommend Alan's review. Alan is an excellent communicator. He's written some wonderful textbooks on real-time systems, and I think he's done a great job of selecting topics to cover in this.
Yeah, I have one comment. I think this is about a framework. It's not only for real-time computing systems, but I also see many applications for
manufacturing
systems.
Indeed. It's just a way of looking at systems. It's not particularly necessarily restricted only to real-time systems. Absolutely, I concur with that. So what I want to do now is conclude by reiterating the main points I have tried to make here today and placing this research, this topic, I've actually talked more about problems than solutions, within a larger context concerning the design, analysis, and implementation of cyber-physical systems. I started out saying that after having temporarily receded to the background thanks to Moore's law, concerns of efficiency have once again moved front and center in the hearts and minds of developers of safety-critical systems, which means that it is time once again for scheduling theory to step up and come up with new ideas that allow us to innovate in developing such systems. However, the techniques of scheduling theory are applied to the analysis of models of physical systems, not to the actual systems themselves. This is unavoidable because analysis occurs before runtime and we are predicting runtime behavior. In order to have a good deal of confidence that the conclusions we draw based upon the analysis of the model will hold for the actual physical system, we have to be fairly conservative in the manner in which these models are built. We have to build a significant amount of pessimism into the modeling process. Such pessimism in the modeling process gets expressed during system runtime in terms of reduced utilization of platform resources during runtime. As the systems we build become larger and more complex and the implementation platforms consequently less predictable, less deterministic, the fraction of the computing capacity of the platform that gets wasted in such, as a consequence of such pessimism in the modeling process is reaching unacceptable levels. In response, the real-time and embedded systems community is proposing moving towards mixed criticality implementations in which less critical functionalities coexist upon shared platforms with more critical ones. The idea being that those resources that are provisioned to but remain unused by the more critical functionalities can be used for executing less critical functionalities during runtime. Now, this idea is not in itself new. However, traditionally, less critical functionalities have only been allowed to execute in the background once the computational requirements of the critical functionalities have been completely satisfied. It has therefore typically not been possible to make non-trivial performance guarantees, particularly with regard to timing behavior, to the execution of these less critical and non-critical functionalities. So mixed criticality scheduling theory arose out of the need to be able to make performance guarantees, albeit at lower levels of assurance, to the non-critical functionalities as well. As I have attempted to illustrate during this presentation, in mixed criticality scheduling analysis, a single system whose runtime behavior is governed by a single runtime strategy gets subject to multiple independent analyses. In one analysis, we construct a very conservative model of the entire system, the critical and the non-critical parts. But in this model, we seek to validate the correctness of only the critical functionalities. Next, we construct a less conservative, a less pessimistic model of the entire system, including of the critical parts. And now we seek to validate the correctness of the entire system. This process of being more or less conservative in building a model can be considered along many different axes, often orthogonal to each other. In this presentation, I illustrated two such axes. We attempted to estimate the minimum duration between successive external events to which the system needs to respond. We attempted to bound the maximum duration of time a piece of code would take to execute upon a platform. Many other dimensions can be thought of, can be considered. For every dimension and for every combination of dimensions, it is possible to construct a mixed criticality analysis problem and attempt to come up with techniques for solving it. Some of these problems would be interesting to developers of actual systems, others would just be contrived exercises. There are many aspects of mixed criticality systems that I haven't talked about here today. Perhaps the most important, and therefore one I didn't talk about just because it requires too much time to talk about, is the relationship to certification. It is arguably true that the genesis of this discipline of mixed criticality analysis arose out of a need for certification. That paper by Steve Vestal that I had mentioned that started much of this work arose out of some work that Steve was doing in attempting to come up with strategies for certification of avionics software. The precise relationship between mixed criticality analysis and certification, the possibility of using techniques and ideas developed in mixed criticality analysis to come up with a certification procedure that is less time consuming, less labor intensive, less costly, is exciting a lot of excitement, exciting a lot of members of the real-time systems community, of the certification and validation community today. This relationship to certification had some other implications as well. In this presentation, I assumed that there are two criticality levels defined throughout a system. Functionalities are either critical or they are non-critical. Many certification standards specify more than two criticality levels. A widely used standard in avionics mandates the use of 5 criticality levels. There's this automotive standard that recommends 4. Many of the ideas and some of the results I have discussed here generalize in a straightforward manner to systems with more than 2 criticality levels. To extend some of the other ideas and results, some effort, some work is needed. And finally, to keep things simple during this presentation, I restricted discussion to the sharing in a mixed criticality framework of only one computational resource, CPU capacity. Of course, in an actual computer system, there are so many other resources that must be shared. Developing frameworks that allow for the integrated, synchronized sharing of multiple resources, each characterized by its own unique requirements and behaviors, in a manner that is cognizant of multiple criticalities, is where all the action is in mixed criticality systems today, where all these projects that I've been talking about, these large ambitious projects, have been working on. Some excellent results have been obtained, but there is so much work remaining to be done before we as a research community can feel that we have significantly solved the problem and made the job of building these safety critical systems a lot easier for actual system practitioners. I think I'll stop there. Thank you for your attention. Happy to take any questions.
Excellent talk.
Thank you.
Stupid question, if I may ask. You mentioned that example where the minimum was 3 units for execution, the maximum was 300.
Yeah.
For people who don't know much about how computers operate today, can you give an intuitive explanation why this huge ratio?
Indeed. So that is, that is an excellent observation. Why does that kind of thing happen? Why does the same piece of code take 3 time units sometimes and 321 time units sometimes? And the reason is because what we are measuring there is from the moment the instruction gets loaded into the CPU to the time it actually completes. And depending upon the situation, different things might need to happen. For example, once the instruction is loaded, the first thing that must be determined is, are the arguments in main memory? Are they in cache? Where are they already in a register? If it turned out that we were lucky, they were in register, there's nothing to be done. We just add them and store them into a register, which is also where the output variable was. In the worst case, what would happen is they would not be in main cache, they would not be in L2 cache. You'd have to do an off-memory retrieval, and all kinds of pipelining effects would take place and bad things would happen.
Okay.
And the reason why this matters is as follows. Because of this variation in runtime, today, if you are developing highly critical software, you will forbid the possibility of both these scenarios occurring. You would either require that the variables be loaded before the instruction be executed, or you would require that memory be flushed before the instruction be executed. You gain determinism, but at the cost either of performance or by tying the system developers' hands very tight, telling them you cannot, for example, allow preemption of threads while they're executing. You cannot have different processes coexist. You must go to an execution paradigm where only one piece of code executes, and then only when it completes will other pieces of code execute, despite the fact that your architecture may be capable of executing many threads concurrently. So either you put up with a non-determinism, which is what is being talked about here, or you give up the capabilities of the platform by not exploiting capabilities that were available.
Okay, another question is about the probabilistic models for the critical and non-critical. You want essentially with a finite support distribution for, say, the critical to guarantee that they are executed. But a model for the critical and for the non-critical could be used, I don't know, perhaps it has been used, I think it must have been used, to make probabilistic statements about the distribution of the delay in the non-critical tasks. Are there results of them? I assume there must be such results in the literature.
That again gets to the heart of a very foundational issue that the safety critical community are wrestling with today, and that is the precise role of probabilistic models with regards to safety critical software. And this is the problem. For hardware devices, for the rest of engineering, for many aspects, we have solid probabilistic models built in large part upon the fact that we have had the opportunity to observe phenomena, physical phenomena, and conclude based upon reams of evidence that this phenomenon behaves in this probabilistic in a manner, its stochastic behavior can be modeled by this probabilistic model. The problem with computation is this. Once you develop enough evidence to state that my critical code behaves in this manner, folks go off and change either the compiler or the processor or some other entity in this entire thing. It's been very hard to come up with a consistent body of evidence to support stochastic models for highly safety-critical systems. Having said that, we use these models all the same, but we always feel a little bit uncomfortable. Are we using stochastic models, probabilistic models, to hide our own ignorance, to hide epistemic uncertainty, as opposed to actually representing probabilistic phenomena using probabilistic distributions? And this is unknown. We don't know this. We are basically guessing. Yeah.
Well, I would trust probabilistic models if they are used to make inference on the non-critical functions.
Yes.
While still guaranteeing
Indeed.
using simple upper bounds
Yeah.
for the critical ones.
That is correct. And I mean, that is a completely reasonable thing, and that is indeed being done. So to some extent, what is being done is, so let me step back for a moment and point out that the analysis technique I proposed here is simply this. When you step back, very high up, the mile-high view basically says you have a system, a physical system, and you have to make estimates about its behavior. So what I'm proposing is you make different models at different levels of fidelity, and then you analyze each of the models separately. It's completely legitimate to make these models probabilistic. So we could, in principle, make a probabilistic model that's very conservative for the critical functionalities and a probabilistic model that's less conservative for the non-critical functionalities and do exactly this analysis. In practice, what does end up happening is that you would use deterministic models, pessimistic worst case behavior, to characterize the critical functionalities, and then do extensive observations on what gets left behind, what resources are unused by these critical functionalities executions, and seek to model that stochastically, and then characterize your non-critical functionalities using that. That certainly happens, but I did also want to highlight the fact that, in principle, there's nothing which says we can't also build a more conservative probabilistic model for the critical functionalities as well. To some extent, multiple modeling is an orthogonal issue to whether we went deterministic or probabilistic. Yeah?
Thank you.
Yeah.
Yes.
Just the last statements you made there, talking about some, I guess they were the standards in the automotive and avionics industries. You said there were 4 or 5 different critical levels. I'm trying to imagine what they are. I understand non-critical means
Yeah.
it has to get done eventually, but what are these other in-between levels?
So, for example, in aviation standards, there's the one I listed over here lists 5 what they call design assurance levels, A through E, and each of them corresponds to the possible consequences of things going wrong in that particular functionality. So, in an airplane, for example, if flight control goes wrong, it's a design assurance level A fault. If your audiovisual system goes wrong, it'll probably be a level D fault. Everything gets associated with some level based upon the consequences of failure. There are technical, not technical, there are descriptive terms for each of these. For example, it's said that level A causes loss of the flight, loss of the aircraft. Level B could cause loss of life. Level C could cause severe injury. And then there is a human being, or I guess a societal consensus as to what functionalities correspond to which level. I remember talking with some folks in Airbus, I think it was, who told me that the only thing in an airplane that they thought before they looked into certification that doesn't have one of these 5 levels was the coffee maker, right? Everything else is a level. And then they were told the coffee maker actually does have a level because it has level E, but it also has a level because it could cause fire if, it could constitute a fire hazard. So things are of different degrees of criticality, but everything's critical. And the assumption that is basically made is something like what I said over here, that if it's a high level, highly critical functionality, you make more conservative assumptions about its behavior and guarantee correctness even under those circumstances.
Yeah, those are basically the FMEA levels that they have, right? Lots of mission, lots of flight.
Right.
Well, that I understand, but I'm kind of curious about this because I understand, critical means it's got to get done before the next guy comes in. and non-critical means, it just has to get done eventually.
Um,
But it sounds like if you're going into these other levels, then you're assigning a cost to them, which kind of goes towards Yakov's question of probabilities, minimizing the cost.
That's not quite the way, so there is a possibility of looking at it as a large optimization problem where you're associating cost with everything and trying to maximize value, right? But this is a little bit different because what you're trying to do is you're trying to demonstrate, so suppose we had levels A, B, C, D, and E. You're trying to demonstrate the correctness of all level A functionalities deterministically under level A assumptions. You're trying to demonstrate the correctness of all level A and B functionalities deterministically under level B assumptions. So the assumptions get weaker, but we are not trying to optimize across levels. These are separate requirements. So you're saying that if you were to look at code, if every piece of code executes for the amount is determined by a level A certified Wset analysis tools, then the level A jobs have to complete. If everything executes for no more than their Wsets is determined by level B certified tool, then all level A and level B jobs have to complete, and so on. So it's.
Thank you. I didn't get that. That's good.
So, yeah, thank you.
Any other questions? Right.
All right. Thank you very much.